All right, week 9 of the semester. We are almost 2/3 of the way done. So if you were doing a marathon, the finish line would still be about 8 miles away, 9 miles away. So you'd be somewhere around mile 16 or 17 of the marathon. So you've accomplished a lot to this point, but we still have a lot to do. This module is angular kinetics. And we are switching from linear kinetics to angular kinetics, just like we did with linear kinematics and then angular kinematics. And what we'll do is we'll use our understanding of linear kinetics and apply that to rotational forces, angular kinetics. Angular kinetics is the branch of mechanics where we are trying to understand the influence of force has on rotation. The term that we're going to really build around is the term torque. And torque is a measure of the tendency of a force to cause rotation. Now, as we go into this module, we have some new parameters that we need to understand in order to understand the tendency of a force to cause rotation. And this is really important because we know general motion, which is a combination of linear and angular motion, has a lot of angular motion in human movement. Obviously, flexions, extensions, internal, external rotations, ABA deductions, all joint movements are caused by angular kinetics. And so we really need to understand the tendency of forces to cause rotation and what things influence that tendency, or what influences torque. So we need to obviously dip into our understanding of force as a vector, magnitude and direction describes a force, but now we need to understand things like moment arm and moment of inertia. And then we also need to draw on our understanding of angular acceleration. Now remember, one trick with angular acceleration, the angular kinematics, is anytime we use angular kinematic parameters outside of just doing angular position, angular velocity, angular acceleration relationships, we need to use the units of radians per second squared for angular acceleration. And that's because radians are unitless. And I've done a video on that before, but it's just really critical to know that we need to use radians per second squared once we start talking about angular acceleration. And that's because when we do our unit analysis, radians are unitless parameters. They're a ratio of the radius of a circle and the secant that or the distance that that would be covered in a circle if you move the radius from one position to another, if you rotate it. So you would have that ratio, and it would be distance units over distance units, and that's nothing, and therefore we call that unit a radian. And so when we do our unit analysis, that radian actually gets dropped out automatically when we do our unit analysis. I'll do some of that in these presentations. The other really important part of understanding torque is knowing that it's a vector, therefore it has magnitude and it has direction. But we're talking about rotational direction. And so I've got a video specifically on dealing with how I describe the direction of torque. If I'm in a physics class, I would do something more like what's called the right-hand rule, where I do the cross product of force and moment, and using a right-hand rule, I can identify the direction of a torque based upon crossing a force into a moment, and then the direction the thumb is pointing tells us the direction of the torque. And from a physics perspective, that actually helps a lot when we're looking at the torque direction in that case. In this class, I use a very different approach to understand torque, and I'll explain that because the direction of torque, the way that we do it in biomechanics, is it tells whether or not the force is going to tend to cause a flexion or extension rotation. So I'll go into that detail in that video. So it looks like a lot of videos here, but a lot of these are short snippets because I'm trying to zero in on a particular parameter related to torque. So I've got Laws of angular motion. There aren't really laws of angular motion. These are just an extension of Newton's laws of motion in the linear sense and applying them to the angular sense. That is, if something's rotating, it's going to continue to rotate unless something causes that rotation to change. That something would be a torque. Newton's second law of angular motion would be when a torque acts on about an axis of rotation, it will tend to cause angular acceleration. So sum of torques acting about an axis of rotation, those torques all add up to the product of moment of inertia and angular acceleration, which is a lot like sum of forces acting on an object cause the object to accelerate, F equals ma. But then and then the third law of angular motion is for every torque acting about an axis, there's an equal and opposite torque reacting about that axis. So that we have torques that come in pairs. And again, we just followed that same rule. If we identify the torques acting on the object about an axis of rotation, we can understand that angular kinematic. And so we don't mix our torques on or by an axis. Types of levers, I'll go through this. We have 3 different classes of levers. Here's the first torque equation that we're actually dealing with. Torque is the product of force and the moment arm, and I go into some depth on how to illustrate that moment arm and what we mean by that moment arm. And then sum of torques equals I alpha. I should put a sum sign in here. Symbol sigma, sum of torques equals I alpha. That's the second equation for torque. Then I go into torque direction. Specifically, I spend a little bit of time on moment of inertia. We know what inertia is from our previous module. It's resistance to change motion. It's quantified by mass of the object. Moment, anytime we see that term from here on, is really referring to something in the rotational world, angular world. And so moment of inertia is an object's resistance to change angular motion. And we're learned that this moment of inertia is not just a function of the mass of an object, but how that mass is distributed about an axis of rotation. And then I give some examples of moment of inertia. Then I go into a specific example of joint moment. And joint moment, again, is the same as, it is the same as joint torque, and moment and torque are synonymous. They mean the same thing. Moment is the better mathematical term, but in our world, we tend to use torque just as commonly as moment. I go through an elbow flexion example, and then I also jump right into angular impulse, angular momentum relationship. You've had linear impulse, linear momentum information already. Now we're just going to take that same approach and apply it to the angular world. So it looks like a lot, but it actually moves along pretty good. And then I just go into some torque examples. It's an immersion video, but this is just looking at some different torque wrenches that I have in my garage, if you will. So just to show a practical application. Okay, so this actually will move a little fast, but we're moving fast for this module because we already have our understanding of linear kinetics, and now really the new things are moment arm and moment of inertia in this module, and then thinking about how these forces are causing angular motion. Okay, I hope that helps, and please remember to join the Monday, Wednesday Zoom rooms to dive into these topics a little deeper. Okay, thank you.